In this video, we're going to discuss the multiplicity of states, that is, the number of microstates available to a system of two Einstein solids. And what we're eventually going to be thinking about is, how does this multiplicity vary as I trade energy back and forth? So, for example, if I give more energy to solid A than solid B, how does that change the number of available microstates for the combined system? For our purposes, we're going to have the same number of particles in each of the Einstein solids, but we're going to allow the energy between the two solids to be exchanged. So our starting point is that we have the multiplicity of states, the number of states available to the first Einstein solid and the second Einstein solid independently. This equation is derived in Schroeder equation 2.21, and it assumes that our energy is much larger than our number of particles. That is, that we are in a high temperature regime where we have a lot of energy compared to the number of particles. Okay. And our total multiplicity must just be the product of the multiplicity of each of these states individually, which leads us to this expression for the total number of microstates available to these two systems combined. So for two Einstein solids, the total multiplicity, the total number of microstates with a given distribution of energy is given by this function here. E over n, where E is just the normal Euler's number, to the 2n times QA, QB, the amount of energy in each of the Einstein solids, raised to the n. Where in this example, we are again assuming that the number of total particles in each of the two Einstein solids is n. So our total number of particles is 2n, but each of the Einstein solids has a n number of particles. Okay, and we can rewrite this in terms of just QA. So the idea is if solid A gives energy to solid B, then solid B's energy increases and solid A's energy decreases while leaving the total energy constant. So QA plus QB must equal Q total, the total amount of energy. Okay. So we can just rewrite this in this slightly more explicit form where we have written out the entire multiplicity in terms of only QA. So it's important here that we really only have one independent variable, the amount of energy in QA, because the amount of energy in Einstein solid B is just Q minus QA, right? It's completely determined. Okay, so the first thing that I'd like to do is I'd like to show that the multiplicity function actually has a peak when the two solids share the same amount of energy, which if you think about it just logically, you would expect that to be the case if I just take two solids that are exactly the same size and I put them next to each other and let them trade energy back and forth. I would expect that in the end, they will each have the same amount of energy, right? And so you would think that there would be a maximum of the multiplicity, the most possible microstates, would happen when each of the two solids has Q over 2, half of the total energy. Okay, so to prove that, we're basically just going to take a derivative of the multiplicity function and set it equal to 0. So obviously, these things out front are just constants, so we could just divide both sides. Since we're setting it equal to 0, we could just divide these out if we wanted to. And then when we take the derivative of this function here, we get QA minus QA squared, and we get this here. So we have the option of having either of these two be equal to 0, right? We need this total function to be equal to 0, and that means that either of these two expressions within the parentheses could be equal to 0. This one easily is solvable, and you reach the conclusion that QA must equal Q over 2. Now I just want to take a brief aside and check two things. One is that this term in brackets here in our derivative of the multiplicity with respect to QA can also be 0 to satisfy our condition. And it's 0 under two conditions. Either QA is 0, which means that both terms in the brackets is 0, or if QA is equal to Q, in which case these two terms are the same and they just subtract to 0. In either case, these are the kind of extreme cases of our multiplicity function where we have all of the energy in QA or none of the energy in QA. And in these cases, we know that this is definitely not going to be a maximum of our multiplicity because our maximum is going to be about 50-50, the 50-50 split there. So these are in fact minimums of our multiplicity on the two ends, and we're not really going to worry about those because we're really only going to concentrate on regions around this QA is half of the total energy is in object A, QA is Q over 2. Okay, so if we take the second derivative, we do this just to make sure that our QA equals Q over 2 is in fact a maximum and not a minimum. So what we're looking for is to make sure that the second derivative is negative, indicating that our function is curved downward and that we have hit a peak. So here is our second derivative function. You should double check this for yourself that this is in fact the proper second derivative. And what we will notice here is bringing the term in brackets here. This is just a constant out front. The term in brackets, that when we let QA equal Q over 2, this term here, which I've just brought out from both of my terms here, is just equal to Q squared over 4. That this term here is 0 because we have Q over 2 minus 2 times Q over 2, and that this last term is going to be negative. And the fact that this last term is negative means that the only non-zero term that we have, because this term is 0, is in fact negative, and so we have a maximum of our multiplicity function at QA equals Q over 2, which is what we were hoping for. We find that the multiplicity is in fact at its maximum value when each of the Einstein solids has the same amount of energy. To find out what the function looks like around this maximum, what we're going to do is we are going to let QA equal Q over 2 plus x, where x is some number that's small relative to Q, the total energy. So x could still be a reasonably large number as long as it's significantly smaller than Q, right? So if Q is 10 to the 40, then x can be 100,000 and it's still way smaller than Q, right? So x doesn't have to be like 1 or 2. It could be a reasonably large number. It just has to be a lot smaller than the total amount of energy in our system. Okay, so in that case, we can plug in QA equals Q over 2 plus x into our expression here, and we simplify to this expression. So the next thing that we're going to do is we're going to try to further simplify this piece, assuming that x is much, much smaller than Q. Now that we have an equation for the multiplicity where we allow the energy in QA to vary slightly from its maximum, from the maximum multiplicity value of Q over 2, what we'd like to do is we'd like to basically simplify this equation to make it more understandable and more plottable for us if we want to kind of see the general structure of this equation. So what we're going to do is we're going to take this second expression in our multiplicity and we're going to expand it by taking the natural log. So what we're going to do is we're going to take this second expression in our multiplicity function and we're going to take the natural log of it. And the goal is that there's a few tricks that we can do to simplify natural log functions. So First, what we're going to do is we're going to take the exponent and we're going to move it to a coefficient out front. This is one of the benefits of taking natural logs. Coefficients, exponents become coefficients. Okay, so now we have a natural log of this function, and we can move the q squared over 4 to be multiplied by 1 minus 2x over q all squared. All right, so all this is an algebraic manipulation so that we get an expression of the form 1 minus something that looks like x over q squared. And we're going to like this type of a form because we have already said that x is much, much smaller than q. And so this will allow us to actually Taylor expand. So what we have now is, again, we can take the natural log of two things that are multiplied together and turn them into the sum of the natural logs of each of those things. So we have the natural log of q squared over 4 here, plus the natural log of 1 minus a thing, and that thing is very small. Now, this expression we can actually Taylor expand, and what we find is that when we Taylor expand the natural log of 1 minus something really small, that is approximately equal to just negative the small thing. In this case, the thing that's really small is 2x over q, because x, we've already said, is much, much smaller than q. So 2x over q all squared is still a really, really small value, right? We take x divided by q, that's going to be really small. We square it, and it's going to be even smaller. So we have now turned this natural log into just an expression of x and q. Okay, so putting this all together, we have n multiplied by the natural log of our q squared over 4, just our first term, and our second term has become unnatural logged due to our Taylor expansion. Okay, now we can undo this natural log by taking e and raising it to this power. That will undo the natural log that we took up here so that we can get it back into our multiplicity equation. Okay, so looking back at our multiplicity equation, we have an e over n to the 2n, so that hasn't changed. And then we have e raised to this thing, where we've separated it into two terms around this minus sign here. So e to the ln of q squared over 4 is just a constant. N is constant, q is constant, so we can take this whole thing and just call it q max. So how do I know that I can call these two terms multiplied together omega max, the maximum multiplicity state? Well, that is because if I look at this term here, x is the only variable, and e to the negative something that goes like an x squared, all of these things are going to be positive. So e to the negative anything is going to be a value smaller than 1, which will reduce the multiplicity of any state. So any state that has some value of x will have a lower multiplicity than when x equals 0. If we think back to how we defined x, we defined it as how far QA is, the amount of energy in my Einstein solid A, is from the maximum multiplicity state of half of the energy is in A and half of the energy is in B. So of course I would expect that omega max would be the state in which QA equals Q over 2 and x equals 0. And that's what we find. So we simply write this as omega max, our maximum multiplicity, and then we multiply it by this function here. So this function is called a Gaussian. The Gaussian function looks like a traditional bell curve. So it will be symmetric on either side of its maximum. Its maximum is when QA equals Q over 2 in this case, and x equals 0. By the time we get to x equals q over 2 times root n here, our e to the thing will look like e to the minus 1, right? We have solved for this n equals 2x over q squared equals 1. So when that happens, then this thing looks like e to the minus 1, and our multiplicity looks like omega max divided by e. So our multiplicity will drop by a factor of e when our x takes on this value. Now, this value can actually be pretty big, especially if Q is large and if Q is much, much larger than N. So if we're in a high temperature limit, then this value of X can be fairly large still, but it's still going to be much, much smaller than Q.